Our today's session is based upon fitting of curves, non-linear curves, fitting of non-linear curves, in which we'll be discussing the fitting of exponential curve and fitting of second degree parabola, fitting of non-linear curves. And the first case that I'm going to discuss is about fitting of second degree parabola. Now, this particular portion requires calculation, so I hope you will be able to help me out in doing the calculation from from your end. Now, whenever we encounter a kind of data, then we try to fit curves to that data. Now, in some cases, what happens is that, as I discussed earlier, that when the data is there in front of us, we just look at the data. By visual inspection, we can say, okay, this looks very similar to linear curve. I mean, if I approach to analyze the data from linear point of view, then probably we'll be able to fit a linear curve to the given data. Fitting of the curve to the data actually means that if I draw the curve, if I'm able to draw the curve, then most of the points of the data will fall either on the curve or very near to that. But if my fitting is not good, then suppose the curve is the behavior of the data is non-linear, and suppose the behavior of the data is like this. This is how my data is behaving, and I forcefully analyzing the situation with respect to a linear curve. So definitely we are going to get a linear curve like a straight line. Obviously my points will fall, most of the points will fall, may fall, or will fall far from my theoretical curve, the theoretical straight line. But if my analysis is strong, then I may fit a curve to a given data, which is a straight line curve I am fitting. Then you may find that the data are falling like this. If my analysis is good, 1 or 2 points will lie here and there, but most of the cases the points will be like this, either on the curve or very near to that. So by inspection, sometimes we are able to say that, yeah, this curve looks nonlinear, this curve behaves non-linearly, or this curve behaves linearly. But often it is not possible, because when we deal with a huge amount of data, then the curve is the visual inspection fails. So in that case, we have to do some sort of mathematical analysis to fit and to fit different types of curves to the given data. Now, there are different types of curves. Second degree parabola fitting are there, exponential curve fitting are there, linear curve fitting are there. One type of linear curve fitting is the regression curve fitting. Now, regression curve fitting has already been discussed. Only difference between regression curve fitting and linear, just simple linear fitting, is that in regression curve fitting, we used the concept of correlation, but without using the concept of correlation, we can also fit the curve. We don't have to go for the concept of correlation at all. Okay, there is another way by which we can do that. Now, suppose let's talk about the fitting of second degree parabola. Okay, so you will understand gradually what I'm talking about. So suppose there is a data. Now I can take a problem from the book, but I actually avoid to do so, because in the books problem datas are very huge, and for understanding, I don't want to work with a huge amount of data. It takes lots of amount of calculation, and it's very tedious. So let me define a data by myself according to my wish. My actual objective is to make you understand what is happening, how to fit the data. So we'll work with a smaller quantity of data. So suppose I am taking the data in the following manner. Like this. Okay, this is my data. So So it is obvious that this data is actually not having any sort of practical significance, because this data has not been obtained from nature. This data, who is shouting? Shrideep. Acha, this data is actually has not been obtained from nature. This data has been obtained from this data has I have created. So this data doesn't bear any practical significance. Obviously, something is playing behind my mind, on the back of my mind, and I'm on with respect to that, I have prepared the data. But my objective is to make you understand how to fit it. What we do is that, suppose we need to fit a second degree parabola to the given data. So we will consider, we'll start with a general equation of this sort. We will say, let capital Y equals to A plus BX plus CX square. This is the second degree parabola, be the second degree parabola that will fit to the data. Be the second degree parabola which will fit to the given data. Which will fit to the given data. This is my assumption. It may not be true also. Now, by the method of least square, there is a method which is called method of least square, but this method is not there in your syllabus. In details, it is not studied in engineering course, but this method of least square is the base with which we actually find two or three sets of, as it is required, normal equations. We find normal equations which will help us to deal with the situation. Now, what are these normal equations and why these normal equations are required, that I'm going to explain. This is my assumption that this particular second degree parabola will fit to my given data. But what is missing over here? Here the missing points are A, B, and C. We do not know the values of A, B, C. The situation is a kind of reverse situation. I mean, if I give you a problem like fit y equal to 4x square plus 2, you will be able to fit many points with respect to x, and with respect to x, many such points of y will be obtained, because you have got the formula. But here the data is given, the formula is not given, so we do not know what are the values of A, B, C. But we know, if I assume y equal to A plus bx equal to cx square, A plus bx plus cx square, then if I can find A, B, C, then this is my hypothetical second degree parabola which may fit to the given data. So there are three unknowns actually. These unknowns are A, B, and C. To find three unknowns, we need three equations. We all know that. So these three equations that will help us to find the unknowns, which are actually the constants, which are actually treated as constants. These equations are called normal equations, and which can be derived by the method of least square. Now, I'm going to show you an easy process to remember the normal equations for the fitting of second degree parabola. First of all, I'm going to write the normal equation 1. Normal equation 1. You will write the equation as it is: y a plus b x plus c x square. Okay. Normal equation 2. You multiply both the sides by x. So you will write xy is equal to a x plus b x square plus c x cube. And then you multiply, this is, we need another equation because we have three variables. So we write normal equation 3. You multiply both the sides by x square y. You will write a x square plus b x cube plus c x to the power 4. Now you put summation sign. Put a summation sign preceding each of these quantities like this. These three equations are called the normal equations. Three normal equations which we will be using to calculate the quantities A, B, and C. These are the normal equations corresponding to the second degree parabola. And remember, how many items are there? If there are n items, if there are n items, then summation A will always give you n into A, because this quantity A is getting added with itself n number of times. So this quantity here, in place of this quantity, we can write NA. And here you can take A outside the summation sign, because A is constant. So we can take this as outside the summation, we can take this outside the summation, just like we did in case of B and C. Now, these are the normal equations. These are the three normal equations. And according to the normal equations, I'm going to prepare my chart. The chart where I'm going to do the calculations. Okay. So we have this data. Let me write the data once again. X, Y. What are the data? 1, 2, 3, 4. 1, 3, 4, 5. Okay. 1, 3, 4, and 5. And Y is 2, 10, 17, 26. 2, 10, 17, and 26. Okay. Now what we need summation Y, summation X. These two quantities we need. So summation X is 5 plus 4, 9, plus 3, 12, 113. This is my summation X. So summation X has been obtained. And what about the summation Y? Summation Y is 2 plus 10 plus the 12 plus 17 plus 26. That is 55. So summation Y is 55. What else we need? We need from here in this summation Y we have got, summation X we have got, we need summation X squared. So we will introduce another column which is X squared. We will introduce another column which is X cube. We'll introduce another column which is X to the power 4, because all these quantities are there. X squared, X cube, X to the power 4. All these quantities are present. So 1 square is 1, then 9, then 16, then 25. X cube is 1, 27, 64, 125. And this would be 1, then 81. And this would be 256. And that would be 625. Okay, so we have got these values from here, and consequently the sums can be also calculated. So summation X square, which is 25 plus 16 plus 10, that is 51. Summation X cube that we are getting is 125 plus 64 plus 28, that is 217. And summation X to the power 4 will be 625 plus 256 plus 82, that is 963. 963. Okay. What else do we need? So this is obtained. This is obtained. Summation Y is obtained. Summation X is obtained. Summation X square we'll find. We need two more things. One is XY, and then another is X square into Y. Then our job will be done. So we'll introduce those columns also. XY. So XY means 2, 30, 28. No, not 28. Sorry. 4 into 17, how much? 68. And 5 into 26, 130. So this is my summation XY column, whose total is 130 plus 68 plus 32. So 230. And the last column that we need is X square Y, which is 2, which is 2, 90, and then 17 into 16, that is 272, 272, and 26 into 25, that is 650, 650. And therefore its summation is summation x square y. So this becomes 650 plus 272 plus 92, which is 1014. Now we are going to substitute all these into the equations. So these are my equations. These are my equations. So we are going to write the equations one after another. So the first equation is summation y. Summation y means 55. So we are going to write 55 is equal to NA. How many items are there? 4 items are there. So it will be 4A. B summation x. B summation x means 13B. So plus 13B plus summation x square means 51C. Summation x square means 51. So it will be 51C. This is my equation 1. My equation 2 is summation xy. Summation xy means 230. So let us write it over here, 230. A summation x. Summation x means 13. So it will be 13A plus B summation x square, 51B. Then C summation x cube, 217C. 217C. And number 3 is summation x square y, that is 1014, and A summation x square, 51A. 51A plus B summation x cube, that is 217B. 217B plus C summation x to the power 4 is 963C. 963C. So this is the equation. This is the set of equation. And you need to calculate this set of equation to find A, B, C. Now, can you do it? This is the question. I ask all of you to find this by any rule. You can apply any matrix method or cross multiplication method or substitution method, anything by which you can take some pain to calculate these values for A, B, and C. If you can find the values of A, B, C, then your second degree parabola will be obtained. Okay, so just try this particular thing whenever you find some time. Try and find A, B, C. Now my data is actually 1, 3, 4, 5, 2, 10, 17, and 26. Now with the help of Excel, how can I use Excel to find the shape of the data? Let me see whether it is indeed the second degree parabola or not. Okay, so I'm stopping the share. I hope you have taken the screenshot of this. And I'm going to put my values in the Excel sheet. I want to check whether my data is indeed a second degree parabola or not. How does it fit? Just wait. Okay, and let me put the values x and y. 1, 3, 5, 4, and 5. 4 and 5. And this is 2, 10, 17, and 26. First of all, what we need to do is to find a scatter diagram for this. Scatter diagram, don't think the scatter diagram is related to correlation always. It is related to bivariate distribution. So this is my scatter diagram. Looks like my job will be done by assuming it to be a second degree parabola. So this is my scatter diagram. Okay. And now if I click on the points and if I fit the trend line, here it is by default linear is being selected. So we want to change it. Our option is to fit a second degree parabola. So we will go for polynomial of second degree. Okay, of degree 2, and we'll display the equation on chart. Close. And you see, if your calculation is right, you are going to get this sort of equation from the calculation, because you see, I actually gave you the value like this. 2 is actually 1 square plus 1. 3 is actually 9 square plus 1. This is actually, sorry, not 3 square plus 1, 9 plus 1. This is actually 16 plus 1. This is actually 25 plus 1. So when I said the data, that was actually creating on the back of my mind. Okay, so therefore, I gave you the data in this manner. But if you do the second degree, if you do not fit the second degree parabola to the given data, then what we will get is, if you fit the straight line equation, if you fit the straight line, let's see what happens. Suppose I'm fitting the straight line, what will happen to the given data? It will fall like this. Only one point, no point will fall on the line. Every point will lie here near the straight line, but not on the point, because my data is behaving non-linearly, not linearly. So this is the difference between the two. Please join once again in the next session for at least 10 minutes.